Okay, now we are on tube now.
Yeah.
Okay, so shall we start? Okay, so hello everyone, good morning, good afternoon, and good evening. So welcome to today's complex fluid and soft matter seminar. So our today's speaker is Dr. Xiaoting Liu. So as a short introduction to about Dr. Liu, so he holds the position of postdoc associate at MIT, and he earns his PhD in 2019 from MIT, and his master and the bachelor from 2013 and 2010 from Tsinghua University, and his PhD research focuses on fundamental problems associated with mechanical failures of soft materials, and his research mission is to leverage molecular design and theoretical modeling to develop high-performance soft matters for long-term healthy care and sustainable water harvesting. So with that, let's welcome Xiaoting for his work. Xiaoting, you can start now.
Okay, thank you, Joanne, for your kind introduction. Okay, let me share my screen. Okay. You can see my slide, right?
Yes, we can see you.
Okay, okay. Thank you. First and foremost, I'd like to thank Joanne and Jen for your kind invitation, and it's my great honor to present actually some of my recent research progress and the results on extreme soft materials. Actually, today I'm going to talk about two aspects. One is relevant to long-term healthcare, and the other one is relevant to sustainable water harvesting. And the fundamental mechanism actually essentially is about how to rationally design soft materials based on Polymer-netw design. Okay. So a brief introduction of my background. So I'm currently working as a post-associate in Department of Mechanical Engineering at MIT. So hopefully I'm going to be an incoming assistant professor in September soon. Yeah, I will let you soon. So a brief introduction of background. So the material I'm going to talk about today is one class of emerging soft material. So especially for this series, many of you might be very familiar with is hydrogel. Okay, so hydrogel can be actually commonly observed in daily life. For example, many tasty food like tofu and jelly are essentially made of hydrogel. And you may also see hydrogel in many different kinds of biomedical products, such as coupling agent for the ultrasound imaging and the super absorbent particle for a baby diaper. And from the fundamental side, hydrogel is a multi-component system, right, with a full of rich physics. So it's basically mainly composed of two components. One is the interconnected polymer network, giving its stretchable elasticity, and the other one is a large quantity of water molecules infiltrating this polymer network, which provides its diffusive-like liquid nature. So due to this unique combination, hydrogel shows many interesting multi-physics phenomena associated with mechanical, electrical, thermal, and chemical coupling. So basically, this is a multi-physics system. And also due to this multi-component systems, hydrogel actually demonstrates broad impacts from personal healthcare to sustainable water energy nexus. So the most common application of hydrogel is its biomedical usage, right? So in these applications, it typically actually requires the transportation of water molecules between the hydrogel matrices and the surrounding tissue environment. So this is epidermal wound dressing made by tough hydrogels, which can accommodate the large deformation of the human body. And then it can actually achieve this programmable drug delivery based on the measured temperature profile at specified locations. And more recently, hydrogel are also being used in an open environment. So where the water can either evaporate or condense into the surfaces of hydrogels. So this is a porous hydrogel, actually hydrogel-based solar vapor generator. So what people found is when subject to light, so the evaporation rate actually can exceed the theoretical limit. And we recently actually provided this theoretical interpretation to understand actually this so-called photomolecular effect to explain this unusual, actually super high evaporation rate of the porous hydrogel subject to light. Okay, I do not have time to go to details. If you're interested, actually we can have some more discussion about this phenomenon. And in all these applications, actually mechanical and physical properties play an indispensable role. Okay, and these properties are also usually actually typically governed by the properties which happened at different length scales. For example, from single chain nanometer scale to natural topology meso scale and to this bulk material macro scale level. And currently, actually, there exists a barrier between different disciplines, which prevents a cross-scale understanding, thereby limiting the space for reaching the extreme property for software materials. So, for example, for people more focused on solid mechanics, actually, in solid mechanics, more focused on continuum level calculation and modeling, continuum level modeling. However, for people in polymer physics, more focused on single chain level calculations. And the understanding of how mesoscale features affect the broad properties actually has been less appreciated by either field. So my research actually is trying to leverage interdisciplinary approach to achieve a cross-scale understanding for software materials. Okay, so in particular, I have been focused on fundamental problems and the translational challenges at the intersection of polymer science, solid mechanics, and advanced manufacturing. So in particular, I work on 3 research areas. So my first research area is to use experiment and the theory to understand the structural property relationship with software materials. So for example, I'm trying to understand how the molecular defects affect the bulk properties. Okay, so my second research direction is to develop this fatigue-resistant hydrogels, which has been a long-lasting challenge since the pioneering work of the double-network hydrogel by Chain Entang Scission. And we leverage versatile manufacturing technique such as electrospinning, 3D printing, and 2D patterning to engineer spatial distribution of crystal domains of in some materials at different length scales. Okay, and what we found is by engineering or by optimizing these crystal domains, we can further push the limit of the fatigue threshold for software materials. And my third research direction is to by further harnessing this high-performing software material as a platform, and to develop 2 kinds of technologies. One is long-term biosensing technologies, and the other one is sustainable water harvesting. So in the interest of time of today's talk, I would like to focus on 2 stories centering on extreme property software materials by Polymer-netw design. So in the first story, I'd like to discuss the mechanics for design tough and fatigue-resistant hydrogels. Okay, and in the second story, I would like to discuss how to rationally design hydrogels with enhanced sorption capacity. And the hydrogel with enhanced sorption capacity will be highly useful for family-scale freshwater production. So let's start with the mechanical properties. Materials with high toughness are highly desirable, right, in many engineering applications. So, for example, steel, concrete, and wood are common structural materials for building construction. And in addition to these common building materials, tough hydrogels are regarded, actually explored as a novel material system for building new building technologies such as smart window with tunable light transmission and the building envelope with evaporative cooling. And the lifetime of these building technologies actually is determined by the mechanical robustness of the hydrogels. And also, hydrogels are also widely being used as the key components in robots, in electronics and devices. Okay, so we recently systematically summarized the versatile hydrogel machines, which actually explore the hydrogel, tough hydrogels as the key structure components, and we systematically discuss the correlation between these targeted function properties of machines and the required hydrogel properties. But here's one challenge. So for most hydrogel actually machines, they suffer short lifetime. So here are two specific examples. So the first example is ingestible hydrogel pill. So currently, the lifetime of a hydrogel-based gastric retentive device is typically actually shorter, is less than 48 hours. And the short lifetime actually is mainly attributed to two factors. Okay, so the first factor is mechanical disruption force, and the second one is due to this severe acidic environment, which is produced by this human stomach. Okay, and my mission is to enhance the mechanical properties so that we can possibly to extend the lifetime for existing gastric retentive device. Okay, the second example is this optical fiber, okay, which has been actively used as this effective tool or light depleting tool targeting deep tissues. But unlike this neuron probe, actually this sciatic nerve actually inactively experiences repeated large deformation, especially when the animal actually is active moving. And this repeated large deformation actually eventually will induce mechanical failure of the fiber. And the question is whether we can make the optical fiber more durable so that actually it can accommodate this large deformation for this sciatic nerve so that it can achieve this long-term light delivery in dynamic organs. Okay. So the message for this slide is design tough and fatigue resistant hydrogel are critical for extending lifetime. And the underlying physics behind this this application actually essentially governed by two quantities. One is the fracture toughness gamma, the other one is fatigue threshold gamma naught. Okay, so these two quantities are essentially fracture energy, which is defined as the energy required for separation of the material into two or more pieces, and the unit is joule per meter square. And the difference between these two quantities is the fracture toughness is defined as the fracture energy measured on the one-time loading. Okay, and the fatigue threshold actually is defined as the fracture energy measured cycle loading. So these two quantities actually can also be understood by this plot. So let's do an imaginary experiment. So we have many samples. Okay, so for each samples, they will experience a cyclic preconditioning with the controlled cycle number. So the fracture energy measured under the first cycle is the fracture toughness gamma. Okay, and the fracture energy actually is likely to gradually decrease and eventually reach a steady state value. So the steady state value of the fracture toughness is the fracture energy actually is the fatigue threshold of the material, and which is also named as the intrinsic fracture energy of the material. And based on the literature, what people found is fracture toughness gamma is usually much larger than gamma naught. Okay. So the first question I'd like to answer is I first want to explain why hydrogel are intrinsic brittle or why gamma naught is relatively low. So let's first understand this glass, which is known to be brittle. The reason why glass is brittle because the fracture toughness of glass is equal to the energy for fracturing a layer of atomic bond. Okay, so graphene actually is a very interesting 2D material, but graphene is also brittle, and the reason is actually recently Professor Chunlo and Professor Ting actually at Georgia Tech, they use experiment and MD simulation to validate graphene also actually follow this graphene theory. But for elastomers, actually that is different. Instead of fracturing a layer of atomic bonds, So the fracture of elastomer essentially actually is associated with the scission of a layer of polymer chains. Okay, and the intrinsic fracture energy of elastomer will be amplified by capital M times compared with this glass or graphene. So here capital M actually denotes the number of monomers in one polymer chain. Okay, and for hydrogels, due to the low volume fraction of the polymers, actually the intrinsic fracture energy will be reduced by the phi to the power of 2/3. So the here phi is the polymer content. So by putting the real number of a real physical parameter for this hydrogels, we actually can estimate the intrinsic fracture energy of hydrogel is typically on the order of 10 joules square. This is actually a pretty low number. You can just imagine. So you just think about it. For metals, the fracture toughness is typically on the order of 10 to the power of 4 or 5 joules per meter square. So then the first question we want to answer is, can we enhance the fracture toughness of hydrogels from a relative low number gamma naught to a relative high number gamma that is compatible with elastomers? Okay. So the first mechanism actually dates back to Jianping Gong's double network hydrogel. So which actually requires introduction of a giant hysteresis. So the double network hydrogel actually contains two networks. So one is the material contains two networks. One is long chain polymer network. The other one is short chain polymer network. When the material is deformed, so the long chain network actually is the floppy. They can highly deform, but they maintain intact, has no damage. Okay. However, for the short chain network, they are relatively stiff. They are inextensible, so actually they experience this so-called progressive damage. Okay, that actually essentially is the key mechanism for this large hysteresis loop as manifested in this nominal stress versus stretch curve. Okay, so let's think about it. So when the material, what happened during this loading unloading process? So when the material is deformed, both the short chain and long chain network and the short chain network actually bear the mechanical load. However, once the material is unloaded, since the majority of the short chain network actually is braked, they actually lose their load bearing ability, therefore giving a reduced, much reduced stress level. So we denote the enclosed area of this loop as a UD, so which basically is the dissipated energy per unit volume of the material. And we further denote the enclosed area of the loaded curve as U, which is the stored energy density of the material, and the ratio between UD and U actually defines the hysteresis ratio of the material. So this is the stretch-dependent variable. So the higher the stretch, actually the higher the hysteresis ratio. So we denote H max as the maximum hysteresis of the material. So the message I would like to deliver in this slide is breaking of short chain network actually gives a high maximum hysteresis ratio. Then the follow-up question is how the presence of the bulk hysteresis promotes high toughness enhancement. So here is what happens at the molecular level. So for double network hydrogel, so first and foremost, actually, it also involves the scission of the long chain polymer, a layer of a long chain polymer network, which actually contributed to this gamma naught, as I just explained. But this is still a relative low number. However, as the crack properties, they are existing a process zone. And for the material inside process zone, they experience this loading unloading process. Okay. So this loading unloading process actually is associated with this breaking of the short chain on the network. And given the size of the process zone, actually we can estimate the contribution of this breaking of the short chain network to the total toughness, which is equal to the multiplication of UD times LD. So conceptually, the total toughness is equal to gamma naught times the gamma D bulk. Okay. And we later actually derived the scaling equation. So what we found is the total fracture toughness is essentially actually can be estimated by three critical parameters. One is gamma naught intrinsic fracture energy. The second one is Hmax, maximum Hysteresis ratio, and the third one is alpha. Alpha is also a dimensionless parameter which characterizes how fast of the material transits into the high dissipation domain. And the alpha actually a promise one for highly stretchable materials. And indeed, actually, we developed a more detailed model. For example, we adopted this Ogden-Roxburgh model to capture the Mullins effect in softer materials, to capture this large high hysteresis in materials. And also, we even developed a micro-mechanism model, which can capture both this Mullins effect and the viscoelasticity in double network hydrogels. So we also implemented this model in this Mullins effect in finite atom simulations. Basically, we actually use the cohesive model to capture the scission of a layer of polymer chains, and also we incorporate this Mullins effect to capture this high dissipation domains. And here is a path of comparison. So the both material actually experiences the same loading curve, but the only difference is for the first simulation, actually the unloading curve follow the exactly same path as the loading curve. However, for the second case, the unloading curve actually experienced much reduced stress, thereby giving a giant hysteresis. So what we found actually is due to the presence of the hysteresis, actually toughness can be amplified by more than 10 times. So the message here is a high hysteresis ratio gives a high toughness enhancement. Okay. So far, actually, this is actually nothing that is special, because actually, especially for metals, for plastics, people know that actually introducing bulk hysteresis actually will be able to enhance toughness. But here is something interesting. What we found something actually exceptional case. Okay. So what we found is actually in entangled polymer network. So the toughness enhancement actually does not rely on large hysteresis loop. Okay, so here's the result. So what we found is, so this is the nominal stress versus the stretch at the different stretch level. Okay, so we can see actually the hysteresis ratio is really small. Actually, even when the stretch level reach up to 13.8, and the maximum hysteresis ratio is about 0.05. And based on this bulk dissipation model, this toughness enhancement should be no more than 1.05. Okay, but our experiment result found actually the ratio between gamma and gamma 0 is 16 times difference. So that means there must be some new physics behind this entangled polymer network. We actually really want to understand what's behind this intrinsic material system. So here's our understanding. So what we argue is, so there are also two processes, and the first process is still the scission of long-chain polymer network, which contributes to gamma 0. But in addition to that, as the graph propagates, there's another dissipation process. So you can just think of how difficult to pull a chain out of this entangled polymer network. Okay, so what happened actually? There are two processes. One is to pull out of chains from this crack plane, from this this primary chains, and also for the these adjacent layers, multiple adjacent layers, there will be local damages. So there will be more layer of polymer chains will be evolved in this scission polymer chains. And recently, actually, Professor Quentin Castino used this mechanical chemistry to visualize the delocalized demo chains in entangled elastomers. And they actually, this is crack plane. So the color actually indicates the density of damage chains as a function of the distance around the crack plane. So as the damage actually can be delocalized up to 100 micrometers. And we denote the contribution from both the pull out of chains and the delocalized damage of chains to so-called near crack dissipations, and denote as gamma dtip. So the total toughness in entangled polymer network actually is contributed by two parts. One is gamma naught, and the other one is gamma dtip. Then the question is, why the entangled network or why the near crack dissipation actually does not involve bulk hysteresis. So here is our argument. So what happened is for the material actually around the crack tip, okay, they actually experience extreme large deformation. And the pull out of chains and the delocal damage of chains actually, if it requires extreme large deformation, which actually can happen, which can occur around crack tip. However, for the material away from this crack tip, the deformation actually is not large enough to reach that threshold. So they actually experience this elastic deformation. They actually do not experience either pull out of chains or delocal damage. Actually, that is the reason why near crack dissipation does not involve bulk hysteresis. And intuitively, we came up actually the third method, so extreme toughening mechanism. So basic idea is, what about integrate both toughening mechanism? One is bulk dissipation, relies on this large hysteresis loop, and the other one is near crack dissipation by harnessing this entanglement. So in this case, actually, it would be possible to actually achieve this different dissipation mechanisms at different length scales. For example, as highlighted by this green domain, what happened is this bulk hysteresis dissipations, for example, by breaking this short chain network. However, as highlighted by this pink domain, this entangled polymer network will play a critical role. So the material we want to introduce is this interpenetrating network based on polyacrylamide entangled network, and the other one is a alginate short chain polymer network. So this is a typical fracture experiment. So we can actually, from the experiment, we can clearly see actually how the material is, the crack first is blunted, and the material actually is, sorry, let me play. So the crack is first blunted, and the material is so tough that actually can effectively retard the crack propagation. Here, actually, we use the tough hydrogel bonding to robustly bond the hydrogel with glass substrate. But even that, actually, we can find that actually the interface between the material and the substrate detach or breaks first before the entire extension of the crack tip. Okay. So the material actually contains only 10% of the polymers, and the fracture toughness can reach up to 2,000 J/m². So it's a very tough material. And we're trying to understand the mechanism in the material system. So we first actually characterize the intrinsic fracture energies. So what we found that this intrinsic fracture energy gamma naught is pretty low. Okay, it's lower than 100 J/m². So this is actually as expected, as I just explained, using this Lake Thomas model. Then we first actually systematically characterize the fracture toughness of this entangled polyacrylamide. So what we found is the hysteresis ratio is low. And despite this low hysteresis ratio, the fracture toughness actually can already show an enhancement for about 5 times. So that is due to this near crack dissipations. And we further introduced the controlled amount of this alginate. So what we found is, as the increase of the alginate concentration, the hysteresis ratio of the material actually increased accordingly. Okay, and the bulk hysteresis actually also increased, and the toughness actually can reach up to 2,500 J/m². And also, the fracture toughness actually increases as the concentration of the alginate increases. So the material system basically actually leverage the synergy of the entangled polyacrylamide, which provides the near crack dissipation, and the short chain alginate network, which provides this bulk hysteresis dissipation. And we further derived this direct model, and unlike this bulk dissipation model, and we have to introduce a new parameter beta to account for this near crack dissipation. So here the dots is the experimental results. The solid line is the theoretical curve. So we can see our theory can capture these experimental results. So here's another interesting results we summarize. So I summarize basically nearly all the data, all the toughness enhancement for all reported sulfur materials. Okay, so toughness enhancement is defined as the ratio between gamma and gamma naught. So fracture toughness actually has been measured by many materials, but gamma naught actually is just measured recently. So the dashed line is the bulk dissipation model. So what we found is for most of the sulfur materials, actually, so the bulk dissipation model basically underestimate this toughness enhancement in most of sulfur materials. So we envision that. So what is missing is actually the entanglement actually is present in majority of the materials. Okay, so this actually is something missing in previous models and in previous understandings. And so far, I think we are recording the relationship between fracture energy and the cycle number. Now we can understand the difference between fracture toughness and the fatigue threshold. So the difference between fracture toughness and the fatigue threshold actually is due to the two parts. One is bulk dissipation, and the other one is dissipation by chain entanglement. And unfortunately, actually, this dissipation eventually actually decreases to 0. Okay, as the cycle number increases. So this naturally actually brings up the second question, right? How to enhance the fatigue threshold? Okay, how to enhance fatigue threshold so that we can actually develop material that can sustain the severe mechanical loading for a prolonged cycle numbers. So here's the motivation. So this is on the water swimming robots developed by colleagues lab, developed by Ji Liu. So he is currently a faculty at the South Tech University. So this actuation actually requires this cyclic stretching of this rubber band, and at a certain point, actually this rubber band fails. Okay, so this is because this rubber band actually reaches its fatigue limit. And similar to this rubber band, the tough hydrogen actually also suffer this fatigue failure. So what we found is, so as I just explained, the reason is the fracture toughness for tough hydrogel actually can reach a high toughness, right, above 1,000 Joule per meter square. However, as the cycle number increases, eventually the fracture toughness actually decreases to a very low level, fatigue threshold on the order of 10 Joule per meter square. Okay. Then the question is, how can we enhance this fatigue threshold? So we have actually tried very hard for this amorphous network. In a double network, hydrogen does not help. For interpenetrating network, eventually still give a low number, and we also try entangled polymer network is also gives a low number. And then we came up. What about introducing high energy phases, such as nano crystal domains? Okay, so the idea is. So our hypothesis is the cracks, the fatigue-induced cracks will be impinged by this intrinsic high-energy phases, such as nanocrystal domains, and it does not propagate over cyclic loads. So here's our preliminary data. So we show that actually this fatigue-induced crack propagation actually versus this applied energy rate, so the measured fatigue threshold can enhanced dramatically up to 1,000 Joule per meter square, once we introduce substantial crystal domains. And we're trying to validate this hypothesis. So we first actually collaborated with Professor Chain Entang at the Syracuse University, and we simulated two companion cases. So the first simulation is we try to simulate the energy for pulling out of chains for crystalline domains. So what we found is the energy for pulling a chain for PVA crystals is much higher than the energy for fracturing a single PVA chains with the exactly same number of units in the polymer chains. Okay. And our simulation actually showed that pulling a polymer chain out of nanocrystal domains requires a much higher energy than fracture single polymer chain. And I also performed systematically experimental calculations to validate this hypothesis. So I fabricated a series of materials actually with the same amount of polymer contents. The only difference is I changed the fraction between these crystal domains and amorphous domains. So what I found is as I increase of the precision, actually the fatigue threshold increased accordingly. And this is an imaging of the fatigue-induced crack measured on the first cycle and measured 3000 cycle. So we can see actually the crack tip actually does not show actually basically no difference. And the resolution, the applied energy rate here is 1000 J/m². Okay, and the resolution here is 30 micrometer for 1 pixel. So given these two, actually, we actually have confidence that introducing high energy physics such as nanocrystal domains will be highly beneficial for enhancing fatigue threshold. Now, then the second question, actually, we're trying to implement this principle for the other design mechanisms. For example, here, we further leverage this principle for developing this fatigue-resistant hydrogen adhesions. So hydrogen adhesion has been also attractive field, but the problem is hydrogen adhesion also suffer fatigue-induced failure. So here, we actually introduce this ordered crystal domains anchored on the glass substrate. So what we found is by anchoring ordered crystal domains, actually we are able to enhance this fatigue threshold from 10 J/m² to 800 J/m². Okay, and we actually demonstrate this robust coating material as an interface material to interact with this load-bearing biological tissues, and we actually systematically characterize wear and friction properties. We are pretty confident actually the introduction of the crystal domains can effectively enhance the fatigue threshold. However, I know many people are actually working on biomechanics and the load-bearing biological tissues. If we're looking into this hierarchical and heterogeneous structures, so we know that actually it's not that simple. It's not just about introducing crystal domains. It's really about how to engineering the hierarchical and the heterogeneous structure in this crystal domains in softer materials. So we further actually leverage different kind of manufacturing techniques such as electron spinning, 3D printing, and 2D patterning to engineer the spatial distribution of crystal domains at a different length scale. So this is a nanofibrous hydrogels. Okay, so the structure actually is this polygon structure, and so we demonstrate actually superior high impact resistance by this microparticle impact test. So for the sample, even after this cycle loading. So this is a collaboration work with Case Nielsen at chemical engineering at MIT. Now actually going back to these applications. So we are fortunate to further actually demonstrate two close to real applications by leveraging this fatigue-resistant hydrogels and the hydro adhesions. So we first actually developed this use this fatigue-resistant hydrogels to extend the lifetime for hydrogel-based ingestible hydrogel device. Okay, so we collaborated with Professor George Vassell's group, and this is actually a large animal test. We successfully demonstrated 30-day retention, and we further actually incorporated this temperature sensors. We demonstrated a 30-day temperature sensor recording. So this is a 1-day temperature sensor, which can clearly show this dietary activity in this pig model. But what is missing is actually is how to analyze this large quantitative data we have collected. This actually is an ongoing work. So in this regard, actually, in my future, I would like to collaborate with data scientists actually to analyze this large quantitative data. So the second actually application is now actually we further implement this fatigue-resistant hydrogels to develop inherent durable optical fiber. So we collaborate with bioengineers, and so we here actually we demonstrate this 30-day optical stimulation of sciatic nerve in a mouse model. So my contribution actually for this collaboration is really to provide this high-performing material as a platform so that either for this fundamental study in neural engineering, neuroscience, or for this translation applications. Okay, so in the second part of my talk, I would like to actually focus on how to rationally design this polymer-network architecture for design another property, sorption capacities. Okay, so water scarcity actually is a global challenge faced by many of us. Okay, currently actually typical method actually include membrane dissolution and membrane desalination. And I would like to actually take a different approach, so-called atmospheric water harvesting. Okay, and the reason why this technology is becoming an emerging technology is there are two reasons. The first reason is the amount of the fresh water in air actually is about 6 times compared with the fresh water in rivers and the lakes. Okay, and the second reason is the amount of air actually, the fresh water in air actually is present regardless of these geological conditions. Okay, so probably due to these two conditions, actually developing technologies that can achieve atmospheric water harvesting has been regarded as the actually emerging technologies for low-cost family scale drinking water technologies. So currently, there are 2 kinds of sorption materials. So the first one is nanoporous sorption materials. Basically, actually, is based on this nanoporous condensation. So, so conventional sorption materials such as include silica gels, which we may commonly see as a desiccant in many products, and the metal organic frameworks. So one unique feature of metal organic framework is, so MOF actually can achieve a relative high water uptake at relative low humidity level. Okay, for example, at a relative humidity level at 20%. But the problem for both silica gels and the metal organic framework is the sorption capacity actually is pretty low at a low humidity or at a high humidity or at a moderate humidity. Okay. So the other sorption material is the hygroscopic, such as calcium chloride. Okay. This is the dehumidifier you may also see from this market. The sorption capacity for salt actually can be high, but the problem is the salt actually tend to form these crystalline structures. Therefore, the transportation of the water into this salt actually is pretty slow. So actually suffers slow kinetics. And also due to the high affinity between the water and the salt, the energy for harvesting this clean water actually requires a high energy consumption. So these actually are 2 drawbacks for hygroscopic salt. So then the goal of this project is to develop novel materials for addressing limitations for existing sorption materials. So I'm interested for hydrogels for this kind of material, new class of sorption materials as well. So here's the working mechanism. You can just think of hydrogel as a sponge, okay? But the difference is the pore size in sponge is relatively large. It's actually macro pore size. But the pore size for hydrogel is typically on the order of 10 nanometer or 100 nanometer, okay? So what happened is because of the hydrophilicity of the polymer network, so the polymer actually tend to attract large quantity of water vapor from this surrounding environment. And the polymer network actually swells, okay? And further by subject to specific stimuli, either in the form of light or thermal or heat. So the water eventually can be either squeezed out, okay? So this is basically the process how the hydrogel can harvest the water from air. So there are actually 3 benefits. So why a hydrogel can be beneficial? First, actually different from this metal organic frameworks or zeolite. Hydrogel is scalable. It's easy to manufacture to a large pieces. And also hydrogel contains high water content. So this actually give people the confidence that it can achieve high sorption capacity. Second, actually hydrogel actually is possible to achieve larger design space by manipulate either this Polymer-network architecture or engineering these function groups. Okay. While this actual field is quite actually emerging, and many actual high-profile paper has been published in recent 5 years. So what I would like to point out is pure hydrogen actually suffer low water uptake. Actually, is in fact actually is inferior to metal organic frameworks, inferior to silica gels, and inferior to salts. So this I think is something missing in the field. So let me first use the experimental theory to understand this. So I use the ideal network. So basically, is a material system free of molecular defects and contains mono dispersed polymer chains. This actually is a very interesting material system for many interesting physics phenomena. If you're interested, you can check my recent actually papers. I won't be able to go to details. I would like to discuss more for the Q&A session. And for the theory, actually, I adopted this Flory-Rehner theory. So basically, there are two physical processes. One is the mixing between the polymer and the water. So this is the driving force, right? It's a favorable term for achieving this high water uptake. But on the other hand, actually, due to the swelling, due to the stretching of the polymer network, so the elasticity of the polymer chains actually is the penalty actually suppress the water uptake. So these two eventually actually determines the sorption capacity at given the relative humidity level. So the red dots, so the black dots is the measured data. So the red curve is the theoretical curve. Actually, we can see at a high humidity level, the theory actually can really agree with the experimental result, which is the typical in the domain of the swelling. Many people have been studying in for that domain. However, for humidity at a low humidity level or in the medium humidity level, the experimental result is much lower than the theoretical prediction. So what is the reason? So here's our argument. Okay. So what we argue is what happened is the polymer chains is not in a highly collapsed state. Okay. Is not in a highly extended state, amorphous state. Actually, it's in a highly collapsed state at room temperature at a low humidity level. For example, we actually here use atomic simulation to simulate the structure change of the PEG hydrogel from collapsed crystal state to this extended amorphous state. And I also use the DSA calculation to characterize the crystallinity actually can reach up to 62% by weight ratio. Okay. So here is another interesting phenomenon. So what we found is, so for most of the materials, so when heated, so ideally it should have a lower sorption capacity, right? Because actually water at a high temperature actually tend to evaporate or tend to dehydrate. So what we found for this PG materials actually is very interesting. It has a high sorption capacity at a high temperature. Okay, so what's the reason? So we first developed this thermodynamic framework. So we're trying to actually understand this physical process in the controlled temperature and also in a controlled relative humidity. So basically, there are four actual physical processes. So in addition to the mixing between amorphous chain and water, and also this entropy elasticity has been covered by this Flory-Rehner theory. And I also include the other two terms. One is the melting of the crystal domains, okay? And the other one is condensation of water. Basically, we need to account for this phase change in the system. This is different from this swelling, okay? And to solve this problem, basically, we're trying to impose the chemical potential of the water in the gas state is equal to the chemical potential of the water in the hydro state. And by solving this specific actually chemical potential in hydrogel and also the chemical potential for of the water in the gas state, so this is eventually equivalent governing equations. By putting the real number for PG network, we actually can solve these equations at different temperatures, right? So we basically can calculate the water uptake as a function of temperature. So here actually we control the humidity at 50%. Okay. So the red dots is the experimental measured data, and the black curve is the Thre calculation. What we can find is at a relatively low temperature, so we indeed observe enhanced sorption capacity as the temperature increases. However, when the temperature is further increases, actually the sorption capacity decreases accordingly. Okay, so that is due to actually when you further increase the temperature, this sorption capacity actually eventually is actually this dehydration is dominated. So given this fundamental understanding, actually we further trying to propose molecular engineering approach. The first one is the so-called introduction of the plasticizer. So here we introduce this glycerol as a plasticizer, and the glycerol actually has a high boiling point, and the glycerol actually is also miscible with this polymer we used in the Hydrogel system. And the idea is we to introduce this plasticizer so that it can actually maintain this amorphous polymer chains even at room temperature at a low humidity level. Okay. And here actually we further actually perform this mechanical calculations. So we can see as we increase the amount of the glycerols, the material actually becomes softer and become more stretchable. Okay, so this actually gives us the confidence that the presence of glycerol actually is able to suppress the crystal domains or preserve this floppy amorphous polymer chains. And we further show that actually as we increase of the fraction of the glycerols, the sorption capacity or water uptake indeed actually increase accordingly. The second approach is so-called we're trying to actually engineer defects. So recording the theory for from this Flory-Rehner theory. So for the mixing term, given the same amount of the polymer and the water, actually we have little space to engineer. However, actually we can dramatically reduce the penalty for elasticity. So here actually given the same amount of the polymers, we can dramatically reduce the elasticity by introducing defects. So here's some actually preliminary results. What we found is as we increase these defects, the swelling ratio actually increased dramatically. This actually gives us the confidence it will be possible to engineering defects to further enhance this water uptake or sorption capacity in Hydrogel systems. So with that, I'd like to conclude actually my today's talk. So basically, I talk about two stories. So centering actually essentially about how to rationally design Polymer-Network, but for designing two properties. So in the first story, I discussed three toughening mechanisms to tough the material, and also I discussed the principle for enhanced fatigue threshold for hydrogels, and also I discussed the two translation applications based on this fatigue resistant hydrogels. And in the second story, I discussed how to rationally design this Polymer-Network architecture for achieving this sorption capacity. In particular, I discussed the two molecular engineering approach. One is the Plasticizer introduction, and the other one is defect manipulation. Okay. So with that, I would like to thank my supervisor, Professor Xuanhe and Professor Gang Chen, for their instruction and the guidance. And I'd like to also thank all my collaborators. And also I'd like to thank the funding agencies. So without this support, it will be impossible for me to actually proceed for these applications and all these fundamental studies. And also I would like to thank you for your attention and welcome for any questions you may have.
Yes, so thank you, Xiaoting, for giving this very fantastic talk on polymer design. So I think it's time for us to open the discussion session. So if there is any question from the audience, please feel free to unmute yourself. And in fact, I do get a first question from the chat box from Professor Michelin Abbas. So she was asking I think her question is about your part 1. So she was asking what would be the interest of using the very stiff, the hydrogels, compared with using elastomers.
That's actually a good question. It's a very good question. I think let me answer in this way. So the most common application of Hydrogel actually is still so-called about the human-machine interface. We try to actually leverage the softness of Hydrogel to interact with low modulus of human tissues. So that's why in majority of cases, actually Hydrogel need to be soft. However, actually for the most actual non-applications, especially for water energy nexus. So in these applications, so actually people require the Hydrogel need to be stiff, need to be actually less deformable, so that actually it can be more actually can maintain shape. Basically, is won't be affected by this environmental stimuli or environmental factors. So, and also for many composite design, Hydrogel actually need to be strong. It's not actually need to be soft. So these actually some application I can think of. And also for some load-bearing tissues, especially for example for biological tissues. For example, many people I think of potentially we can develop, for example, tissue replacements. If we think about the mechanical properties for tissues, they are typically actually experiencing this J-shaped curve. They are actually the stretchability is not that large. The modulus actually is typically is about 100 megapascal. So in that scenarios, actually that actually requires high toughness, high strength, but not that deformable. That's high stretchability. Yeah.
So basically, through your polymer network design, you can control a large variability of your like stiffness and also toughness. Right?
Yes, different parameters.
Different application.
Yeah, different parameters. Yeah.
Yeah, that's good. So Zhao Xu, I think you may have a question for Xiaoting. Yeah, feel free.
Yeah, Xiaoting, I think a great talk. Yeah, it's great that you summarize all the excellent work you have done and some of the recent works that you were doing. So I have two questions I think that may interest to the public here. I have some other questions, so if you are available, we can talk after the meeting.
Absolutely.
The first quick question is, I'm just curious how you measure the intrinsic, the fatigue threshold. So did you gradually increase that cyclic stress and take the maximum stress without crack propagation? Second question is, you mentioned that you introduced nanocrystalline domains that seems to increase the fatigue threshold quite a lot. I'm just curious whether that can also increase the fracture toughness. So whether they increase the crack tip dissipation as well as bulk dissipation as well by just introducing those nanocrystalline domains to the polymer network.
Sure. I think basically are two questions. The first question is how to measure intrinsic fracture energy or fatigue threshold. Okay. The second question is what's the impact of crystal domains on toughness? Okay. So let me first answer the question number one. So let me use this image. So what do we do? Basically, we actually perform two tests. So the first test is we need to perform this. Let's first start with the sample with notch. Okay. Then we need to have the camera to monitor the crack extension. So when we apply a low stretch, actually, then if you apply very extreme low stretch, the crack does not propagate. Okay. As you gradually increase the stretch, the crack propagates at a certain point, and eventually you can measure the crack extension rate. Okay. And for different stretch is corresponding to so-called energy release rate. But to calculate the energy release rate, we need another test. We need another sample with no notch. Okay. And apply on the same stretch level, do the cyclic loading. And when the stress level reaches a steady state, then we can actually calculate the strain energy density stored in the sample. So with that, actually, eventually we can plot the cracking extension rate as a function of energy release rate. So from that plot, you can imagine as the energy release rate is low, that is 0. And as when the energy release rate is high, it gradually increases. And we use the linear aspiration to identify this transition point. that threshold is the intrinsic fraction energy or fatigue threshold we identified from experiment. Okay, so for more details, actually you can check for our papers. We actually mentioned the details for the experimental calculations. The second question is about the crystal domains. So the impact of these crystal domains actually for toughness is not new. Actually has been studied for a lot. So the basic mechanism absolutely will enhance toughness. The basic mechanism is by melting of the crystal domains. And what happens is by melting of the crystal domains, it actually will provide this large Hysteresis loop. So then the presence of large Hysteresis loop will dramatically enhance toughness. This actually go back to my first part of the discussion, why the presence of Hysteresis loop promotes high toughness. So this is how the crystal domain enhances toughness. Yeah.
And how does the melting of the non-crystalline domain come to play? So you mean that during the stretching, there will be internal deformation of the...
So melting the crystal, basically what happens is you can think of basically basically can be pulled out of chains. So this is one process. Also, so one chain, something like this, essentially basically breaking the hydrogen bond between the this neighboring polymer chains in the crystal. So the breaking of the hydrogen bond actually dissipates energy.
I see. Yeah, thank you.
Okay, so Yu Hai Xiang, so please feel free to unmute yourself and ask your question.
Hi, Sorry. Thank you for your fantastic talking. Yeah, I have a question now. I think it's page 29. It's about the hydrogel adhesion. Yes, I understand you if you introduce the crystalline into the hydrogel to increase the fracture toughness, but how can it increase? I mean, also will be help for the adhesion because you didn't change the substrate, right? You have to actually measure the adhesion between the substrate and the hydrogel.
Yes.
Because there's no crystalline in the substrate, right? You just introduce some crystalline into the hydrogel, so you still can increase the the adhesion. What's the reason? I feel it becomes
let me explain. So the failure mechanism for detachment or for this hydrogel adhesion, there are two processes. One is so-called adhesive failure, or the other one is cohesive failure. So adhesive failure means basically is the failure at the interface. Cohesive failure is the happen at the material. Okay. So if it happens at the cohesive failure, then basically essentially is still the design the material. The same, basically essentially the same as the material. So what happened is actually, if you look at this schematic, what happened is this these crystal domains actually they form extremely strong hydrogen bond with the substrate, especially with the glass substrate. Okay, so in that case, actually due to this synergistic process of this strong hydrogen bond and surrounding this high crystal domain in the bulk of materials, so that actually will achieve a high fatigue threshold. Okay, so that essentially actually we measured actually from 10 to 800. So this is our measure result, and we also actually use the X-ray scattering to characterize this this gradient structure happen actually from the substrate and as a distance away from substrate. And also what we found is from many actually biological system, one is the for example from this soft tissue, this muscle tendon, this connective tissue to the tendon, they also contain this actually similar ordered structure that from this bone to this soft tissue. So interesting actually this this crystal structure is actually very useful, actually helpful for this adhesion energy at the interface. So this is actually my kind of understanding for this high interfacial process.
You mean actually the adhesion also matter, right? The hydrogen bond should be very strong.
Hydrogen bond should matter, and the material is also matters. Eventually, is the synergy of these two.
Okay, thank you, Xiaoting.
Yeah.
So one more question from Wei. Please unmute yourself and ask your question.
Okay, thank you. You know, the schematic models you showed in many slides, So these models illustrates the morphology and the distribution and even the entanglement.
Sorry, I cannot hear some of yours.
Can you hear me?
I can hear you, but I cannot hear some of your words. Can you repeat again? Yeah.
Oh, okay. Maybe the connection is not very good. So
yeah,
in many slides you show the schematic models of hydrogel. That's that represents the the morphology, the distribution, and even the entanglement between the short polymer chains and non-polymer chains, right? So I just wonder I just wonder whether there is an experimental method to verify or to validate these models.
Good. So let me put a few. For example, you mentioned entanglement, right? We did perform this rheological calculations to characterize the different kinds of entanglement. Okay, and for crystal domains, we also did characterize, for example, use the DSA to measure crystallinity, and we also performed scattering to characterize the number density to characterize the distance between crystal domains. We also characterize the orientation of crystal domains. So we so the general answer to your question is that we have to adopt versatile structure and the material calculations to understand this structure of the materials. Yeah, that's how we eventually arrive at these molecular architectures.
Okay, thank you.
Yeah.
Okay, next question from Hyste. Please unmute yourself.
Hello, can you hear me now?
Yes.
Yes, we can hear you.
Okay, I have a very general question about the water uptake.
Great. Sure.
Using hydrogels, because we know that the water states in hydrogels can classify into three different kinds, right?
Yes.
Once you use the hydrogels to uptake the water from air, I'm wondering, can you guess what is the state of water after uptaken into the hydrogels?
Okay, that's a good question. My answer is basically there are three states, right? Actually, the three states, for example, is a free water, bounded water, and intermediate water. Actually, that depends on the distance between the water to the molecular chain. So my understanding is my current hypothesis, I haven't really rigorously studied this problem, but this is a good question. Since currently the amount of water can be absorbed by water or absorbed by water by hydrogel is relatively low, especially at intermediate water content or low humidity level. In that case, it's most likely is the bounded water. Is most likely bounded water. However, if your hydrogel contains salt, for the calcium chloride, then it can actually uptake a lot of water. In that case, it can contain both. It can contain all three states of water. This is my understanding for the water state in hydrogel for water uptake. Yeah.
Okay. Thank you.
Okay, so Shaoting, I think I can give you my last question, in fact, about the synthesis of your polymer hydrogel. So since you can have a well-controlled like polymer chain structure, so I'm just curious how you can control that pattern in your synthesis process.
So let me just use this ideal network as one example. Okay. So this ideal network, I didn't discuss too much about this material system, right? This material system is very interesting. So this material is one example. This actually contains AP type of macromers, and these each type of macromer, they cannot react with themselves. They can only react with each other. So in that case, actually, eventually they will be favorable for forming this alternating 2D structure, but in three-dimensional is a tetrahedron structure. And people actually also perform these multicolor simulations actually to quantify different kind of defects in the system based on the concentration of the macromers. And given this actually understanding and the preliminary study, eventually we can really well control. For example, in the first step is really to eliminate the defects in the system. And the next step is readily control this defects in the system. So for me, actually, I demonstrate capability for controlling the Entangled chain defects in the system, basically by controlling the hydrolysis of the ambidextrous group. Yeah.
Okay, thank you very much for your further explanation. I think with that, we can close our today's seminar. And thanks to Xiaoting for giving this great talk. And next week, we're going to have another interesting talk, and hope everyone can get back for our weekly seminar. And hope you can have a great resting of your week. So that's stop here. Thank you all.
Yeah, thank you. Thank you for joining.